You are given a fraction x upon y, and in one operation, you can either increase the numerator by 1 or decrease the denominator by 1 if the denominator is not already 1. Your goal is to maximize the value of the fraction after doing exactly one operation. And if this problem sounds too easy for you, then you might want to try out the harder version of the problem where you are allowed to do exactly k operations on the fractions and then maximize the final value of the resulting fraction. Keep in mind that you are not allowed to simplify or reduce any of the intermediate fractions. That is, for example, if you transition from 3 upon 7 to 3 upon 6 by decreasing the denominator by 1, then you cannot simplify this 3 upon 6 to 1 upon 2. You should keep the fractions as is, and then at the end, when you are computing the decimal value of the final fraction, then you can either normalize it, simplify it, or directly do the long division and then figure out the decimal value. So this is the premise of the problem F, sum of fractions, from Codeforces Round, Codeforces Educational Round 188, which was rated for Div 2. In this video, we will incrementally develop the solution to this problem by first starting with a very simple O of n to the power 4 solution, and then piece by piece making some optimizations to reach n cube log n time complexity, then n cube, then to n square log n, then to another version of n square log n from a different perspective, which can finally be optimized to n log n. If you are interested, there is also an O of n solution to this problem, which I will briefly talk about in the later sections of this video. So, in order to help you assess the correctness of all of these easy versions of these problems, I have created a custom contest on Codeforces that also has similar practice problems as well for you to submit these uh, easy versions of the problem. So the details of these contests will be available in the YouTube description, and that same description will also have my code for all of these versions so that you can look at the code and see if whatever you have implemented is correct or not, and then you can even submit your own code on Codeforces for automatic judging. If you are a beginner, you might think that you don't need to upsolve a problem F from a div 2 round. But I promise you that no matter at what level you are, there is some section of the video that you might find relevant. For example, if you can come up with the O of n cube solution all by yourself, then I would highly recommend you to at least watch till the part of n square log n. Basically, if you can go till level X all by yourself, then you should watch the video at least till level X plus 1, or at least till the point where things become too difficult for you. So that is how you upsolve, and then you learn a new concept from upsolving the problems that is out of your comfort zone. So let us start with the easiest version of the problem. So notice that in the problem description, even though I have specified the rule for a general x upon y, the problem actually simplifies things for you and says that the starting fraction will always be 1 upon b, where b is a positive integer. So let's first focus on the case where you are only allowed to do the operation once. Then in that case, if increasing the numerator is beneficial, then this is the fraction that we will get by increasing the numerator, and then this is the one that we would get by decreasing the denominator. And if increasing the denominator is indeed beneficial, then this inequality might hold. right? It should hold. And if you simplify this further, you will get that this inequality is always correct for b greater than equal to 2. And we know that if b is equal to 1, then of course the only legal move is to transition from 1 upon 1 to 2. So this makes it clear that mathematically it is optimal to always increase the numerator by 1 whenever you have just one operation. So now let's go to the harder version of this problem where you are allowed to do exactly k operations. So you might think that, okay, at each stage it is beneficial to increase by 1, increase the numerator by 1. So if you are allowed to do k operations, the answer should be 1 plus k by b, right? Because at each stage you are making the best possible choice that you can get. But is this idea correct? Can you prove it, or can you find out a counter example to prove that it is not correct? Notice that we already proved it mathematically that this is always correct when k is equal to 1. But then what is the proof or the counter example when k is not equal to 1? So this is where the concept of greedy versus DP comes in. So notice that the solution that we have just derived is kind of greedy, right? You are making the best choice by considering only one operation, right? So that is why greedy is the best choice at the stage that you are currently at. But what dynamic programming says that it is sometimes okay to make suboptimal choices at a local region so that you can get a greater payout at the end. For example, uh, you can either keep on going step by step and then getting the maximum value at each step, or you can take some lower amount of values at each step but then encounter a ladder and then directly jump to higher floors, right? So this is one scenario where you can see that sometimes even if you accept a lower payout at the beginning, at some point you will reach a stage where you can jump to a higher payout scenario, while this one will continue accumulating lower payouts, so it will not get the benefits at the end, right? So notice that even though it is beneficial to increase the numerator by 1 to get the maximum value of the fraction, but the problem never asked us to maximize the intermediate fractions, right? All we care about is that the final value of the fraction should be maximum, right? We don't care if the intermediate value becomes less, right? We are only interested in the final value. So you might think that, okay, this greedy approach is definitely not working. So there must definitely exist a DP solution to this problem, and it might be difficult to come up with, right? But this is not always true, right? Whenever your greedy approach doesn't work, it doesn't mean that there is a complicated DP approach. In fact, this is one of the skills that you have to enhance to grow your rating on Codeforces, wherein you start with any greedy solution and then explore why it didn't work, and then can you tweak it to make it work, right? If greedy is not working doesn't mean that DP will work there, right? Maybe an alternate greedy solution that you did not encounter in the first pass, that might work, right? So let's not give up our hopes on the greedy yet, and let's analyze why will greedy not work and what is the counter example, right? If you have some suspicion that greedy is not optimal for the final result, let's figure out what is the counter example, right? So if greedy is not working, then you must be doing some, like, let's say, decreasing of the denominator at some stages, right? So let's try to find out whether there is a alternate greedy approach, or there is a way to prove that the greedy that we have come up with, which is increasing the numerator at each stage, whether that will always be correct for us given set of scenarios if it doesn't work for in general, right? So this is where the power of visualization comes in, right? While dealing with the numerators, we only dealt with mathematical formulas and then we came up with this closed form expression, which is fine, right? But we also need to have some intuition about the problem and then visualize what exactly is happening. So since we have already done some mathematical analysis on the numerator, let's visualize that on a number line, what exactly it means to do those operations in succession. So this is the number line and this is the fraction that you start with, which is 1 upon b. In one operation you go to 1 plus 1 by b, which is 2 upon b, and then you keep on going to the right. So now you can notice a pattern. In each stage you increase the numerator by 1. So after b minus 1 stage, you will eventually reach b upon b, right? And keep in mind that b upon b is not equal to 1. Like I already clarified in the video earlier, that b upon b is not equal to 1. So what will our strategy be if we start at b upon b, or if we reach b upon b after some set of operations? So it might be difficult to see what will our strategy be. So we'll come back to this problem after visualizing what happens when we try the decrease operations first, right? But now here you will notice that I have applied all the increase operations in succession. I have not intermixed the increase as well as decrease operation. But it doesn't matter because because the problem only said that you can keep on increasing the denominator by some value and then keep on decreasing the denominator by some value. And since reduction was not allowed, then the final result will have to be of this form, right? You decrease the denominator d times and then the remainder of the times you increase the numerator. So this is the first crucial observation that you can make, which is the order of the operations does not matter. That is, you can either do all the decrease operations first and then do the increase operation, or do all the increase operations first and then do the decrease option. So just from this observation, we got the idea that we can club all the decrease operations together and the increase operations together, right? And this is how it came to my mind that we have to notice the transition when you keep on doing all the increase operations in succession. So in order to make progress on any difficult problem, you have to come up with some invariant or some observations about that problem and then build upon it, right? So just by looking at this ordering does not matter, we came to this conclusion, and just from this conclusion we came to this number line, wherein we saw that if you keep on going we will eventually reach b upon b, where something special might happen, right? Even if it did not occur to you that something special might happen at b upon b, that is fine. In the next slide I'll talk about how you can spot this. Okay. So what happens if we instead do the decrements first, right? In the previous slide, we saw that we did all the increments first and then we reached b upon b. But what if we do all the decrements first? So if you do all the decrements first, then you make this transition from b to b minus 1, then to b minus 2 and so on. And then after b minus 1 steps, you will eventually reach 1 upon 1. So notice something interesting. After b minus 1 operation, you are at 1 upon 1 in the decrement strategy. And in the increment strategy, you are at b upon b. So even if you did not notice this special scenario of b upon b, it should immediately strike you that at least in the decrement case, it is obvious that at some point you will reach 1, and after that, after reaching 1, the strategy is very clear. Why? Because you can only increment the numerator by 1 as per the rules. So even though our greedy might not work in general, but we can say for sure that if you have reached an integer value, or more specifically 1, then your greedy approach will for sure work, because that is the only legal move. Okay, so we have spent b minus 1 rounds to reach 1, right? And notice that all of these were not optimal, right? Because every time we made a transition, we could have instead done a increment and then gotten a better intermediate fraction. But let's compare what happens after b minus 1 rounds. So the decrement strategy has reached 1 upon 1 and the increment strategy has reached b upon b. Now what happens at the bth round? Okay, from 1 you can transition to 2, but from b upon b, since you cannot simplify the fraction, you can only transition to b plus 1 upon b, which is equal to 1 plus 1 upon b. So 2 will always strictly be greater than 1 plus a fraction. So if you can kind of conclude that if you had money to spend b minus 1 rounds, then instead of reaching b by b, it would have been a wise choice to reach 1 upon 1, because it costs the same, but then it gives you the greater payout after reaching 1, right? And as you can see that once you have reached 1, you cannot decrease the value anymore, so there is one strategy. So even though we have not solved the complete problem, we have solved at least some part of the problem. That is, if you have money to spend b minus 1 rounds, better to just do all the decrements, reach 1, and then keep on doing the increments. So that is why we say that if you make some suboptimal choices now, like if you are suffering currently, you can reap the benefits later, right? So this is the same idea behind DP, but this is not exactly DP in that sense, right? I mean, the idea behind DP is also same, that make some suboptimal choices, right? Like you are not getting the maximum benefit here, but at the end you will get the greater payout. So just to summarize, once you reach 1, there is only one operation allowed, and then reaching 1 is as costly as reaching b upon b. So why do you want to waste your increment operation by reaching b upon b, right? So in case things are too abstract for you, I'll just give you a counter example. Sorry, I'll just give you an example to explain what's happening. So if you start with the fraction 1 upon 5, and we have already concluded that the order does not matter. So if we apply the increments operation first, then after 4 rounds we'll reach 5 upon 5, and if we do all the decrements operation first, then after 4 rounds we'll reach 1 upon 1, and then at this point after 4 rounds, this lower strategy will always be strictly greater than the upper strategy, right? So far we have only solved the case that k is greater than or equal to b minus 1, right? But what about the case where you don't have the money to reach the golden point, which is 1 upon 1, right? In that case, should you do any decrement operation, or is it better to do only the increment operation? So your gut feeling might say that it is better to do the increment operation only, because reaching the why are we trying to reach 1 upon 1? So that all the operations that can be done after this point will reap a benefit of 1, exactly 1, right? Otherwise, in the other strategy, by reaching b upon b, you'll reap a benefit of 1 upon b, which is not optimal. Okay, because this fraction will always be less than an integer 1. So your gut feeling might definitely say that, okay, if it is not possible to reach 1, then no point in doing any decrements operation. Just take the greedy choice and then do all the increments operation. So in a contest setting, and if you are experienced candidate, you might have this idea, and then you might like also get the intuition that this is correct and this is actually correct. But what is the proof behind that? Like, can you actually prove that doing all the numerator increases, if it is not possible to reach 1, is the optimal strategy? So that is why we said that if you are not able to reach 1, why do you need to suffer? Why do you need to make the suboptimal choices? Suboptimal choices should only be made if you have some long-term goal in mind. But if you don't even have the ammunition to reach round B, then might as well take the best choice at each stage. So looks correct, and it actually is, but you also need some proof behind it, and not some theoretical mathematical proof, right? You should have some intuition and idea also. So one common idea is known as exchange argument, and in this you try to look at the sequence of operations that are not optimal at each stage, and then you swap out one of the operations by an optimal or local greedy choice that maximizes the local benefits, and then prove that the result will be strictly better or at least as good as the current one. So how can we prove via exchange argument that if it is not possible to reach round B, that is k is less than B, then it is always better to do all the increases only, numerator increases only. So to do that, notice that since the order does not matter, then you can have all the numerator increases in one line, and then all the denominator decreases in one line right after that. Then this will give you a fraction, let's say x upon y. Then let's focus on the last denominator decrease that you have done, and you have run out of uh, money, and then you are not able to make any operations on it. Then if you swap out this denominator decrease with a numerator increase, then the result will be better, right? Because we have just seen that doing numerator increase on one operation is strictly better. Why? Because x plus 1 by y will always be greater than x by y minus 1 if this is actually a fraction which is less than 1, and we are already discussing the case where it is not possible to reach b by b or 1 upon 1. So this inequality will always hold. So that's why you can swap out the last denominator decrease by a numerator increase, and if you keep on following this strategy, you'll be able to prove that you have to increase the numerator in all the rounds if it is not possible to reach the sweet spot, which is 1 upon 1. So this is what exchange argument is. You try to pick one operation, and then you swap it out with a better operation which is a local maximum or optimal choice, and then you demonstrate that the result is at least as good as the current operation that you have. So one interesting thing that you might notice is that this entire problem exists only because of the constraints, which is b upon b not equal to 1 upon 1. And why do I say that this is the only piece that is holding this entire problem together? It's because if you start with 1 upon b, then after b minus 1 operation, you'll reach 1 upon 1 or b upon b. And if these actually had been equal, then you are reaching the same point from both the directions. So might as well reach the point reach the destination point by making the optimal choice at each stage. So that is why if this problem was not, if this condition was not specified in the problem, then it would have been trivial to solve. That is, you always take the increment operation. There is no point in taking the decrease operation anymore. So yeah, at this point, feel free to pause the video and think about all the observations and arguments that we have made. Basically, the exchange argument, the ordering does not matter, and then ordering all the increases first and then doing the decreases, and then concluding that one is the turning point, one is the sweet spot after which everything changes. You see how everything hinges on this one. And how did we encounter one? Not from this b by b. This might be complex and might be hard for beginners to see or catch. But once you started doing the operations, and then once you started playing around with the decrease operations, then it was clear that at some point you will reach one by one, and at that point you might get some motivation to compare it against b by b. So let's formalize everything. If you have at least b rounds of ammunition, then this is the final results that you can make. So what does each term indicate? So you started with 1 upon b. So you will waste b minus 1 rounds to reach 1 upon 1. So how many rounds do you have remaining? The answer is k minus b minus 1. And then since you have reached 1 upon 1, you will add this number of rounds remaining to the numerator. So you do this, and this is the expression that you get, k plus 2 minus b. This is when k is greater than or equal to b. And then if it is not possible to reach the meetup point, which is 1, then makes sense to simply increase the numerator as much as possible. So the rest of the problem will we will base the rest of the discussion on this important formula that you see on this screen, and then we will try to optimize we'll try to come up with an optimized algorithm to implement this formula when b and k are changing. So take a minute to pause this video and think about the correctness of this formula. So now that we have solved the easier versions of the problem, which is we started with 1 upon b, and then we said that you are only allowed to do one operation, and then we said that you are allowed to do k operations. Let's move on to some harder versions of this problem, and we'll see that as we have started gaining intuition, and as we have started visualizing things, then the harder versions that are yet to come, that might not even pose a challenge for us. So let's see. So let's say I give you, instead of previously I gave you just one entry, right, which is 1 upon b, but this time I give you multiple entries, like let's say 1 upon b1, 1 upon b2, 1 upon b3, etc. So you have m entries, and then you are allowed to do the operation on any of the fraction, not necessarily one fraction. You can do the operation on any of the fraction in any of the rounds, and then your goal is to maximize the uh, maximize the total fractions that remain after all the operations, and you are allowed to do k operations in total, and you have to maximize the total sum. So now can you come up with the strategy to solve this harder version of the problem? So you can notice that if you had just one entry, the entire effort went into reaching one, right? Because only after reaching one you can reap the benefits of the full one instead of having a fractional 1 upon b. So will you try to distribute the operations on these fractions, or will you pick one fraction and then first try to reach one? Obviously it makes sense to reach one as soon as possible, right? So how do we reach 1 as soon as possible? There are multiple fractions. So then you can notice that each one takes b minus 1 times to reach 1. So therefore the minimum value of the b, if you have this array b1, b2, b3, etc., then the minimum value of the b will be the candidate that will lead you to reaching 1 faster. So with multiple entries, we have the strategy of picking the bi, let's say b star, where b star denotes the minimum value of b, and then decreasing it down to 1 upon 1, and then doing some operations. Now suppose you reach 1. Suppose you reach 1, then what should you do? Should you then distribute the operations to the other fractions to also make it come down to 1, or should you keep on continuing with this fraction? So you can see that there is no point in decreasing this fraction or increasing this fraction and then eventually reaching 1, because you are just wasting all the intermediate round, right? Because what will you even do after reaching 1? After reaching 1, you will eventually have to do some operations on it and then gain the benefit of 1 at each round. You might as well do it with the fraction that you just invested in, right? So this makes the strategy clear that even though you have multiple entries in the subarray, and even though you are allowed to distribute the operations on any of the fraction in any of the round, the strategy is simple. Pick the minimum valued bi, take it down to 1, and then stick with it. Don't apply that operation to any other fractions on the list. So all the operations will necessarily be done on a single fraction from the list. Now, what about the case where it is not possible to reach 1? In that case, can you prove that it is beneficial to still pick the minimum valued fraction and do the increment operations on it? So if you cannot reach 1, should you distribute? So the answer is no, you should not distribute, because you can simply pick the minimum valued fraction. So for example 1 by 5, and if you want to do the increments, right, then if you want to do the increments, then you can see that 2 upon 5 will be strictly greater than 2 upon 8, right? By the way, ignore this expression over here, because if we can't reach 1, then of course we won't be doing the decrement operation. So I should have compared with 2 upon 5 versus 2 upon 8, but this inequality is still true, right? So now we have our conclusion that no matter how many entries or which entries are present on the array, we have to do all the operations on the minimum valued bi only. And what is the strategy? You pick the minimum valued bi and you start with the fraction 1 upon b star, where b star denotes the minimum valued bi. Then you spend b minus 1 operations to reach 1, and then you stick with that fraction, and then you keep on increasing it. So this is the final version of the formula. So let's take a moment to talk about all the terms that are appearing here, because in the remaining section of the video we will not be discussing any more concept. It will only be about optimizing the implementation of this formula. So we have already seen that for a single fraction, the answer is always k plus 2 by b if k is greater than b, and if k is less than b, the answer is 1 plus k by b. So this is the answer for a single fraction. But notice that the problem had asked you to maximize the total sum. But since we are not touching the other fractions, we still have to take their sum, right? Even though we have not changed them. So this term is nothing but the sum of all the fractions except the one that you chose for doing all the operations. So that is why the total sum minus the value or the value of the fraction with the minimum value of bi. So let's try to implement this. But before we do that, we go on to the final version of the problem which was present in the code forces round, which is this time. So we started with a single element 1 upon b, right? And then we added multiple entries to the array. And now we are making the problem a bit more difficult by adding multiple ki's to the array as well. That is, you need to answer that same question but in a different fashion. That is, you are given one single array and in one query you have to answer that for if you fix k as this k1, then give me the answer across all the subarrays. So this is an example of a subarray. So for this subarray you create the array 1 upon b1, 1 upon b2, 1 upon b3, etc. And for this subarray you give me the answer for this k1, and then you repeat this operation for all the possible subarrays for this array, and then you print the sum for this ki. Then you go on to the next ki, and then you give me the answer for this k, fix this k, then iterate over all the subarrays and then sum it up and then give the result. So you will see that in this version also the logic does not change. It's just that the problem is asking us to do this operation multiple times in a different fashion. So let's go to the implementation. So in the implementation, as we saw that you will be given k as inputs, and then you have to iterate over all the subarrays and then apply this formula. So that's what we do. We take the ki as input and then we iterate over all the subarrays. You can do that by iterating I and then iterating j, and then our goal is to find the minimum valued bi. So you can do that by this O of n function which is called min element. And if this minimum, if k is greater than or equal to minimum, then you apply this formula which I've already added over here, or if it is less you apply this formula, and then you still have to sum up the remaining elements of the array. So how can you do that? You sum up the all the elements of the subarray and then you subtract the contribution of this minimum element, because the contribution of the minimum element has already been counted over here. So the time complexity of this solution is O of n to the power 4. Why? Because there are two loops for iterating the subarrays, and this function min element works in O of n times, and also this sum function works in O of n time. So this is n cube for a single k, and you are given multiple k's in the input. So the total time complexity is O of n to the power 4. So how can we optimize this solution? So one simple strategy that you can see is you are relying on the minimum element of a subarray and then you are relying on the sum of a subarray. So minimum element you can definitely get from a segment tree if you are aware of segment tree. But even if you are not aware of segment tree, no need to skip the video because we won't talk about segment trees in this video. I'll show you an alternate approach which is much cleaner and easier to remember than segment tree. But if you do have the template handy with you, doesn't hurt to use segment trees and prefix sum. So with prefix sum, you can quickly query the sum of a subarray, and with segment tree you can quickly query the minimum element of a subarray. So this is the implementation for the segment tree based approach, wherein I am using the AdCoder library for segment tree, because why do you need to reinvent the wheel when there is already a good enough library out there. So first of all, I converted the array into a prefix sum array and then added this lambda function to get the sum in O of one time. This is a very standard trick. I will not dive into the details of that. And then all I did was replace this min element call with the O of log n call from the AdCoder library. And then I replaced this O of n call to get the sum with the O of 1 call that I just added to get the prefix sum. So this is our first optimization that we have made. We jumped from O of n to the power 4 to O of n cube log n. But can we optimize it any further? do we even need segment tree, or is segment tree an overkill? So that's where another technique comes in, wherein instead of iterating the subarrays in any random order, if you iterate them in a certain order, then it might be easier to compute the value of the minima as well as the prefix sums. So our goal is to figure out, is there any strategy to figure out the range minima without using the segment tree? And yes, there is a way. How can you do that? You start at this index I, and then you quickly compute all these answers of all the subarray that start at this index I. So which subarrays are there? The one ending at this, or the one ending at this, and so on. So how can you, so you are only interested in two things: the sum of the subarray as well as the minimum value of the subarray. So you can start your iteration from here and then maintain a counter for the minima. And as soon as you encounter a smaller element, you update that counter to say that, okay, the element X that I have just encountered will be the new minima. Same for the sum. You start from here and then you keep a running sum. So this is also a fairly standard trick. I will not dive into the details of that. So using just an iteration technique of left to right by fixing the left index and then computing the answer for all the subarrays that start at index I, you can keep track of the running minima and the running sum. So this is the implementation for that. So you see that just 10 to 15 lines of code, no need of segment tree, and we have optimized the solution to O of n cube already. And what is this? We are just fixing I, the same strategy that we discussed. We are fixing I, and then we are keeping a running minima in the variable min, and we are keeping a running sum in the variable sum. And the rest of the formula I have not changed. That is exactly the same. So this is good, but can we optimize it even further, right? Because n cube is not that good of a time complexity. So in the later parts of the video, we'll talk about some different strategy to optimize it. So far, we have seen the strategy of starting with a particular index, or using segment tree, or using a brute force approach. So before we dive into that optimization, I want to talk about a different problem, the solution of which will lead us to the optimization that will be used to reduce the time complexity from n cube to something better. So this new problem says that you are given an array, and this is a subarray of that array, and you have to compute the minimum value of this subarray, and then you have to compute the sum of the minimum value across all the subarrays. That is, for every subarray, you write down the minimum value. For each subarray, you keep on writing down the minimum value, and then you add them all up, and then you print the result. So you have to find out the answer, which is find the range minima of all subarrays. So how can you do that efficiently? So to do that, this trick is also fairly common, although this is something that you might not be aware of. So I will briefly talk about this more, and then I will share some resources in the next slide on how you can learn more about how to solve this version of the problem. So to solve this, we have to change our perspective a little bit. Instead of going with the fancy approach of fixing a left endpoint and finding out the answer for all the subarrays that start at I, we have to think out of the box. We have to change our perspective and think of a way that will help us with this, right? Because because if you keep on sticking to this strategy, then as you are doing this, you can still compute the minima sum, but then the time complexity would still be of n cube, right? You still have to iterate over all the arrays, right? So we are looking for something better. So the different perspective is, you fix a particular index I, and then you ask the question, this particular index, the value in this particular index will be the minimum value of some set of subarrays in which this will be a part of, right? So how many subarrays are they? So if there are 100 subarrays in which this value was the minimum element, then of course this element has contributed 100 into value into the final sum, right? So this is what is known as the contribution technique. You pick an index and then you add its contribution to the final sum in one go, right? But we have to be very careful with that approach, because you might end up having duplicates. So for example, if you see, like if you ask the question in how many subarray the value 2 is the minima, you can see that it is in this this subarray and this subarray. So 2 subarrays, so 2 into 2. And similarly for this value you ask how many subarrays is this the minima in, so it is this and this, so 2 into 2, 8, right? So you might print the answer as 8, but the answer is actually 6, because there are only 3 subarrays possible: this, left, right, and the entire thing. So 2 plus 2 plus 2, 6. So how do we handle the duplicate strategy? So this is also a well-known famous trick, that if you want to handle duplicates in problems dealing with minima, you kind of enforce an artificial rule saying that if you have multiple copies of the minimum element, you will consider only the leftmost element of that leftmost copy of that element as the minima. So you pretend that the minima is unique and the leftmost minima is the smaller in case of type. So with this artificial limitation, by the way, this is something that I apply to all of the problems that deal with the contribution technique, right? So this you can keep in mind. So with this artificial limitation, you can clearly see that if you can somehow figure out how many subarrays will contain this index as the minimum valued element, then the answer would simply be count, which is the number of subarrays, into the value of this, right? So we now we are looking for something different. Now the problem is, for a given for each index, do you have an algorithm to compute the number of subarrays in which it will be a minima? So for this exact problem, I have recently added a, a video on my YouTube channel, and that the problem is exactly that. So the name of the problem is range minimum sum. That was also a 2400 rated problem, but I would also recommend even beginners and intermediate players to attempt that problem, because the techniques that I have described in this problem is very efficient and very easy to remember. In fact, I did not have any difficulty at all while while porting over the techniques from this problem to this problem. So this video talks about a strategy to compute for each index what is the number of subarray in which this element will act as the minimum. So I will not go into the details of this video, but the crux of that video is that you input an array, and for each index it will output 2 red bars for you. So this red bar that you see on this screen, and we are dealing with index I. Okay. So what the algorithm in this video does is that for each index it gives you the location of the red bars, and these red bars indicate NSC and PSC, which is the next smaller element and the previous smaller element. So you can see that for this element, this red bar is the first element to the right, which is smaller than it, and this red bar is the last element to the right, which is smaller than it. Then any subarray which has a starting point that does not touch the red bar, that is after the red bar, like this subarray or even this subarray, and any subarray that ends before touching the red bar, like this subarray or even this subarray, those subarrays will always have this value as the minimum value, right? Because why is that true? Because the only element that is smaller than it is these red bars, and we have said that we are not allowed to cross over the red bar. So if the index of this red bar is L and the index of this red bar is R, then how many possible starting points for the left endpoint of the subarrays are there? that is simply I minus L, and how many possible choices for the right endpoints, that is simply R minus I. So this is actually the total count of subarrays in which this element acts as the minima. So in fact, you can submit this minima problem, that is counting the number of subarrays in which an element acts as a minima, on the custom contest that I had created in this video. But for now, even if you do not know about that strategy, you can still continue watching the video under the assumption that you have computed this capital L and capital R in an O of n fashion, and that will not affect your understanding of the remaining section of the video, right? Because all we need is an algorithm to compute these, and once we have this L and R, we don't care about like how this L and R came through, right? So you can might as well assume that they came from a template just like segment tree. So yeah, that is what I said, that this is just a standard problem for finding the NSC and PSC, and it has two approaches. One is with set, which is very easy to implement, very easy to remember, very versatile, can solve a lot of problems. And then it also has the stack variation, which a lot of people prefer, but not me personally, because even though the stack version is neat, time complexity is O of n, but every month or every 3 to 4 months I keep on forgetting the stack based approach. So I can, if I devote couple of hours on it, I'll be able to write the correct implementation without any bugs for the stack based approach. But if you just give me 5 minutes, I'll write the correct set based approach without any bugs. So that's why I highly recommend you to watch this video as well. Now let's move on to the next part. That is, assume that I give you the location of this red bar, that is capital L, and this capital R. But notice that we were talking about the range minima sum, right? And we have already solved this problem. So now let's go back to our original problem and how do we optimize it. So we still have to optimize this function, right? This function. So this time we don't have to just sum up the values of the minima, but instead the contribution of the minima, right? So we want to talk about how to optimize using the contribution technique of the minima. So the idea is simple. Instead of doing the sum of minima, we want the sum of a function of minima. But if you think about it, there is not really a big difference, right? We had to do this. You simply compute the number of subarrays in which this element will act as the minima. If that is the count, you simply multiply this value by count. You simply multiply this value by count, right? And you simply multiply this value by count. However, you might face one challenge, which is this one. So for each subarray, the answer is some function of the minima of that subarray, as well as all the sum of all the elements of all sum of all the elements in that subarray. So how do you optimize this? Like how do you accommodate for this? Because even if I give you the count of all the subarrays that has I as minima, you cannot simply infer the sum of all subarrays that the sum of elements of all subarrays that has ai as the minima. So you don't actually have to worry about this right now, because this you can find using another contribution technique. Because if I give you a subarray, and if I ask you compute sum of ax, right? And this part you can do by contribution technique. Why? Because suppose you pick this element, then how many subarrays will it be part of? So it has I minus 1 or I choices to the left, we'll have to see the exact thing, and n minus I choices to the right. So this will be part of L into R, left into right, these many subarrays, and then you can simply add the contribution of these individual elements. So you can split this formula into two contribution technique. One contribution technique is the contribution provided by the minimum element, and the other contribution technique is the contribution uh, provided by the individual elements in increasing the sum, right? So this is the implementation. So this store and this alive thing, etc., that you see, all of this is just the template for computing this capital L and capital R, the red bars on the left and right. So you don't have to worry about this. You can look at the previous video, and from this part is the template. This is where the template ends, and from here you can see that once we have capital L, and by definition capital L is the first point which is strictly smaller. Similarly, capital R, we can count the number of subarrays in which this element I is the minima, which will be number of choices to the left and to the right, product of them. And then we simply add the contribution directly by multiplying count, right? We did not change that expression. The expression is same. We are just adding count prefix there, right? And then we also have to add the count prefix over here as well. So we did that. And then we already decided that we'll handle this separately because this doesn't really depend upon the minima. If you think about it, what will this look like across all subarrays, right? This is just the sum of all elements of all the subarrays. Maybe I'm not making my point clear, I think, for this part, but it's trivial to me maybe, but you should spend some time to think about why taking this term out and then dealing with it separately still works, right? So to deal with it at the end, I just simply iterated over all the arrays, and for I iterated over all the elements, and for each element I figured out the number of subarrays in which it will be a part of, which is the number of starting points to the left and number of starting points to the right, and then I added its contribution, which will be 1 upon bi. So with this, the time complexity has reduced to n square log n. And why did the time complexity reduce? Because now we are and now we are not starting at an index and then keeping a running minima or something, right? We are starting at a starting index, but then we are already getting all the information that we need to compute the number of subarrays in which this will be the minima. Okay, so now the final section of the video, and at this point, if this feels too complicated for you, you can skip this part. And yeah, honestly, like this part is the implementation of this part is also very simple and easy to understand, and actually this is actually a good advice and good exercise for you to try out the next part as well. Although yeah, although I won't dive deep into the details of this part, because I'm assuming that if you are reading through this part, then you kind of have the ability to catch on things. So we are just building on the efforts from the previous part. Okay, so we have the same formula as before, right? And this time we want to, so see, in this version we fixed a k, and then we did this operation of iterating over the entire array, and then adding the contribution of each element. But now what happens if the problem gives you multiple ki? Suppose this is k1, k2, k3, and assume that all of them are in increasing order, right? Now the algorithm that we just described, that is O of n square log n. Why? Because this entire thing is n log n, and then there are multiple ki, right? But if you want to optimize it to n log n, then we have to iterate that array, the original array, only once, and then keep on adding the contribution directly to all of these k, right? So that is also another version of the contribution technique. So a lot of things being discussed in this video. So like the first contribution technique that we discussed is how to compute the sum of minima of a subarray across all the subarray. Second contribution technique that we discussed is how to compute the sum of all elements of all subarrays. Third contribution technique that we discussed is how to compute the sum of f of minima over all subarrays. The next contribution technique that we are discussing is if you have multiple ki's, right? How can you find out the answer to all the ki's at once while you are iterating the array? But notice that even though the minima is fixed, but the contribution of the minima heavily depends on the k, on the value of the k, right? The contribution of the minima depends on the value of the k. So if k is not known to you beforehand, then you will not know which part to add, either this part or this part, right? So that's where we introduce a new technique, okay, which is whenever you have a linear function and you want to do some operations on it. So for example, this answer for any given k, it depends on k, and then there are terms that do not depend upon k and only depend on the minima, and then there are terms that are constants. So let's separate out the terms. So we'll just start with this formula only, and we'll split it into two sections. The first section is the fixed part, which is independent of k. That is, every time you encounter a subarray, it will contribute 2 minus b star irrespective of what the value of k is, correct? So we keep 2 minus b star on the left hand side, and then it will also contribute 1 minus b star irrespective of which k you choose in this list. So this is the fixed component. No matter what the value of the k is, as long as that k is greater than the minima, the contribution will be this. Similarly, for the downward side, you can split this into 1 upon b and k upon b. So you can say that 1 upon b will definitely be contributed no matter what the value of k is, as long as the condition is satisfied. And then minus 1 upon b star will definitely be contributed no matter what the value of k is, as long as this condition is satisfied. Even though this value is 0, I still added it for brevity so that you do not get confused. And what about the variable components, the one that depend upon k? Apart from the conditions, so the variable components are this k, so we have taken it on the right hand side, and here the variable components are k upon b star, so we have taken it upon the right hand side, provided that the conditions are met, right? Now if you are standing at this particular index I, and you are able to compute the number of subarrays in which this element will be the minima, suppose that number is count, then you know that the contribution of this element will be equal to count into this fixed part plus count into this variable part, right? And this count into fixed part will be applicable to all the ki values as long as they are greater than the minima, right? And this ai itself is the minima. So what we can do is, since this k array is sorted, we can find the first entry that is greater than or equal to minima. Suppose that entry is this one, and then we can add this contribution one by one to all the entries to the right? Because all of them, even if you did that operation again with a different ki, the result would be same, right? If you go from this k to this k, the inequality is still satisfied, but the value of the fixed contribution does not change, right? So why do we need to compute it again? So we find out the first element that is greater than this minima, and then we add this fixed part to all of these entries. Similarly, if k is less than minima, that is these sections, we add the fixed part to these. So far so good. But what about the variable part? So for the variable part, you can see that the variable part has a very nice form because this is a linear function. So this is of the format k into some constant that does not depend upon k. So this ai, let me clear the screen in case it's getting a bit. Yeah. So what we can do is, suppose for this element AI, this is the first element that is greater than AI. So all these elements to the right should receive this contribution into count, and all these elements to the left should receive this contribution into count. There is no debate about that. Now, all these elements to the right should also receive a variable contribution, but this variable contribution which will actually depend upon the value written over here, right? So suppose k5 is written or k6 etc is written, because you have to do the product, right? So it will be k5 into count and it will be k6 into count, right? So how do you actually do that? So to do that, you assume that everyone will try to add a variable component into it. So for example, somebody will want to add b1, somebody will like to add k into count 1, and then once you reach a of I plus 1, it might want to add k into count 2, right? And then once you reach a of j, it might want to add k into count 3. So you can see that you can take out this k factor common, and then once you take out the k factor common and you only maintain the coefficients of the k, right? Then you have to add same coefficient to all of them, right? So this product thing now has become a sum, right? So that is the novel idea over here, that you have to notice that everyone everyone adds a different product but to the same variable k, right? So k into x1, k into x2, k into x3, and then everyone wants to sum them up. So you say that, okay, I will multiply this k at the end. Why don't everyone just add their contribution instead of multiplying it? So what you do is, you want to contribute k into count, right? So you just go to each ki and you increment the coefficient count by k. You increment the coefficient count by count. You increment the coefficient by count. And then at the end, when you are iterating over this k array, your answer would be simply fixed contribution plus variable contribution into whatever the value of this k which is written over here. So let's go on to the implementation. I hope that will make it a bit more clear. And yeah, I agree that this part might be a bit complicated, even though it sounds simple for me. Because, so see, all of these ideas, right? Like they seem very, very convoluted at first, but now that I know how to solve them, I think it might be difficult for me to kind of understand uh, what it is like to not understanding how it works and all. But yeah, I would suggest you to spend some time on it, and like maybe even take this for granted, and then run some test cases and see why this coefficient things work. And once you see it, right, once you see how everything fits together, it is very difficult to unsee it, right? And that is exactly what's happening to me as well. Maybe that's why I might not make the explanation very beginner friendly, but at least you have the code, you have the recordings, you can at least go through them couple of times. And I request you to do these operations multiple times on your copy and then get the hang of it. And once you see why this trick is working, you'll remember that trick forever. Okay, so okay, let's go back to that code section. So I have just created a function to add the contribution, because now we want to simply iterate over this array and then add this contribution by iterating over the k array instead of iterating over the original array again and again, right? So I added a function for iterating over L to R and then adding a contribution, and then I created two contribution arrays called fixed and variable, right? And so first of all, we find out the count of how many subarrays in which the AI will act as the minima, basically the left barrier and the right barrier, the red bar on both ends. And then we want to find out the first element which is greater than the minima, right? Because this formula splits based upon how many k's are greater than it, right? So you can simply do that by this lower bound function. And once you have find out the lower bound function, we have already discussed that the functions to the k to the right will receive the fixed contribution from the top half and the variable contribution of 1 into count. So that's why I've written over here. So variable contribution of 1 into count and fixed contribution of the top part that we just saw in the previous slide. Similarly, all the k to the left, they will receive fixed contribution from the left half, which is 0, right? And then the variable contribution from the right half, which is 1 upon b. So this part. So here you can see that in the fixed part, even though it is 0, you might not see it as 0 immediately, but this is actually 0 if you compare this and this, right? Yeah, because we are adding the contribution here as well as here for all the values irrespective of k. Finally, at the end, if you remember, we also had to add the sum of elements of all subarrays. So that part will contribute to all the k's, right? Irrespective of it's to the left or to the right, right? So that sum of elements of all subarrays, that will contribute to all the k's. So left hand side as well as the right hand side. And then finally, to compute the answer, you iterate over the contributions received, and then you sum up the fixed and variable part into the value of the k. So this is the point where you multiply the value of k. Now how do you optimize it? You can see that the final optimization is simple. So right now, to make things simple, uh, I had just created this contribution function for iterating from left to right and simply adding the values, right? But what we need is a fast data structure that can add things to a range, right? What we want is adding something to a range over here and then adding things to a range over here. So you can do that by another data structure called difference array. And by now I assume that you are familiar with difference array. So all you have to do is you keep that signature of that function, but behind the scene you maintain it as a difference array. What is special about difference array? If you add something in a range to a difference array, then only two values would change, because the difference of these two elements does not change because you added the same entry to both of them. So behind the scenes you convert it to a different array, uh, to a difference array, and then at the end you convert it to a prefix sum. So finally, let us look at the implementation of the difference array. It's pretty simple. You keep the signatures same, but every time you add something, you increment over here and then you decrement over here, because the difference of the rest of these, they do not change, right? And at the end you convert it to a prefix sum array, and then the user can query the value to retrieve the actual value. So once you are done with the all the additions, you convert to prefix sum so that you can retrieve the original value, and then you call that same function to print the answer. And you will notice that there is no change involved for the original algorithm, right? Always changed is the internal implementation of this add contribution function that now maintains it via difference array. So it has the time complexity of O of 1 per updates, right? And now the time complexity is O of n log n. And you can see that if we had not taken that set based approach to compute the left and right boundary, the time complexity would be O of n, but actually not really, because you still need to figure out the lower bound, which is the first element to the right, which is greater than bi. So maybe I might have misspoken at the start of the video, but either way, the right now the complexity is n log n, and theoretically the complexity is n log n square, because this problem deals with modular arithmetic, and that involves division, and that division involves additional log n factor, but those are implementation details. So as far as I'm concerned, n log n is the time complexity for this, since I'm using the coder modular int library for doing all the division operations on fractions. So yeah, this is the summary of the problem. Like we started with a very simple greedy approach, then we saw how it worked for a single entry, then it did not work for k operations. Then we made it work by trying to do some operations ourselves and then visualizing what happens. Then we optimized it to ncube login via segment tree at coder library. Then we realized that segment tree wasn't really needed, so we switched to prefix sums, prefix minima, running maximums, running minima, and then we switched to n square login, wherein we added the concept of the contribution technique of using a set to figure out the left and right boundary to figure out in how many elements is AI a minima. And then we saw that we can optimize it in a different form by instead of iterating the k one by one, we iterated the entire array a only once, and then we added the contribution to k. So we switched up our perspective, but when adding the contribution, we simply iterated it over the range of the k, and we added all the contribution. And then finally we saw that optimization to n log n, where we moved this range addition to a difference array behind the scenes, right? And along the way we also talked about how to do updates of a linear function which has the pattern of ax plus b. So to do these kind of updates where x, so if you have x1, x2, x3, etc., and if you want to do ax plus b updates, and as long as all the updates are of this form only, like a1 of x plus b1, a2 of x plus b2, etc., then we saw that you can simply maintain a fixed variable and then take the contribution in that, and then you can maintain a variable for this coefficient part, and then you can sum them up, and at the end multiply x1 into variable plus fixed, right? So these are the all the techniques that we have discussed in the video. So yeah, make sure to solve all the problems on Codeforces, and look at the previous video also that I talked about. That is actually very important. I think this concept keeps on appearing again and again. And regarding the last part, I think maybe I rushed a bit too much on the last part. So if something is not clear on the last part on how the coefficient part etc. is working, feel free to ask me in the comment section, or if you have any different approach, feel free to let me know in the comment section. Thank you.